carry on. Sorry.
Okay. Well, hello everyone. First of all, I would like to thank the organizers for organizing this nice event, and it's been a nice break from the daily routine, just going to these talks and listen to what everyone is working on or thinking about. Also, thanks for giving me this opportunity to share something of my research. So my name is Jaco. I'm a PhD student here in Utrecht in the Netherlands. I'm being supervised by Leonard Meyer. And currently my research has been focused on, or among other things, focused on higher proarrow equipments, which are sort of like a higher generalization of so-called proarrow equipments you might have seen. Well, you studied like two-category theory or just ordinary category theory. So before I start raining down definitions, or I just want to like to introduce to you why you would even care to study these so-called proarrow equipments. So let me change the way I project so it's somewhat better. So let's start with some motivation. So the first motivation comes from equivariant category theory, homotopy theory. So given a finite group G, you can construct homotopy theories which are equivariant. So they are parameterized by the group G. So for instance, one can study spaces which are equivariant spaces or equivariant spectra. These are where this is governed by a group G. And yeah, this turns out to be a quite useful concept. So you essentially you remember some symmetry of the element of the objects you study. For instance, Hill, Hopkins, and Ravenel, they used like equivariant spectra to resolve the invariant one problem, at least up to one case. So I mean, this is one of the motivations, but it turns out that these equivariant homotopy theories fit in a framework of what is called G infinity categories. So this is a framework that is being mainly developed by Barwick, Dotto, Glassman, Nardin, and Xia. And in this framework, they define some sort of equivariant co-limits, equivariant mapping spaces. They come up with an equivariant Yoneda lemma, and this is all very useful. So this is one of the motivations, but when you study category theory, you also see another notion of co-limits and limits, which is slightly different from the usual notion you knew before. Another example is this thing called like relative co-limits and limits. So let's say you have a diagram F, which is fibered over an infinity category C, so depicted in this diagram. Then you can define a relative co-limit or limit of this diagram. And this is done by Lurie in higher topo theory. There's some useful mechanism. For instance, Lurie uses it a lot of times in higher algebra, or he also studied relative adjunctions in this context. So it turns out to be quite useful. So now you've seen, I've just shown you two different kinds of co-limits and limits. And they indicate that there are some category theory going on with these fibered and these equivariant objects that's not really the same as that are quite different from the usual co-limits. So there's some different category theory here. So you can ask the question, so do these two examples fit in some general framework that produces a formal category theory of the objects you would like to study? And the answer to this question is yes. And this already exists classically. So there are many more ways to do this, but one of the ways this was done classically is by studying proarrow equipment. And it turns out that this is quite easily generalized to the higher setting. I mean, all the definitions are essentially the same, but you always have to think about, when you generalize something to the infinity categorical setting, what is the correct way to phrase your definitions, and then you phrase them in such a way that they also make sense higher categorically. So the answer is just yes. So given an infinity 2 category X plus extra structure in the form of an infinity equipment, you can get some formal category theory of the objects in X. So you get a notion of co-limits of maps in X and limits of maps in X, a notion of pointwise Kan extensions, a Joné lemma, a notion of what a fully faithful map should be in X, and some sort of Homestead characterization for adjunctions. So by definition, an adjunction in X is an adjunction in homotopy 2 category, but this is not the usual way you usually check it. So I mean, this way of checking it in homotopy 2 category involves checking some triangle identities, but what you're used to, at least I'm most used to, is checking that that you have some equivalences on mapping spaces, and then you get an adjunction. But while the same holds in this infinity equipment, there's some notion of checking whether things are representable, and essentially this all follows from having a sort of Joné lemma in this context. So I said extra structure, but essentially this infinity equipment also, I mean, it contains the whole data of X, so you can always retrieve X from the infinity equipment. So an infinity equipment is a kind of double category. So let me just quickly recap what a double category is. I think we've seen it a few times during the seminar already, or this conference. So a double category P in particular has objects, which might be a set or a class, or I don't really care about size in this talk, but anyways, you have objects, you have one cells between them, and what is special about a double category is that there are two directions for one cell. So you have a vertical and a horizontal one. So and also a double category has two cells, which can be pictured as these squares that I draw here. And so this arrow A to B, this is a horizontal arrow, and this horizontal arrow, and this two things are vertical arrows. And then essentially a two cell also has some data between them. So essentially a two cell has a source and target, and the source and target consists of a horizontal and a vertical arrow. And then for the target, you also have a vertical and horizontal arrow. And then the double category comes with a compatible associative composition with identity. So compatible here means, I mean, you can compose two cells, but implicitly when you're composing two cells, you're also composing one cell. And you want that when you compose the two cell and then restrict to one of the targets or the sources, vertical or horizontal arrows, it's just the same as composing them right away before you compose the two cells. So this is what is meant by compatible. Well, when you have a double category, you can consider two sort of truncations. So you can first look at the underlying horizontal 2 category, which is denoted by hor of P. So the objects of this 2 category are the same objects of P, and as one cell you take the horizontal one, and the two cells are defined like this. So whenever you have a two cell in the horizontal 2 category, pictured by this thing, then this corresponds with such a two cell in P. So here you have the horizontal arrows, but the vertical arrows have to be degenerate, so they have to be identities. Now you can do the same by replacing horizontal with vertical, but now so you replace this by vertical, and then you have the same picture here, but then you have like some. So this would be the picture of your two cells. So you have degenerate horizontal arrows, and vertical arrows can be anything. So this is briefly what the double category is, and well, we want to do this all high categorically. So in a minute, I will say what the right generalization to the highest setting is. And but first, let's start with an example. So this example is already very important. So this is the weak double category, which we will denote by pro. And this is what is called a proarrow equipment. And we will see shortly why it's called a proarrow equipment. But this double category pro, this has as objects, it has categories. As vertical one cells, it has the functors, and a horizontal one cell is something that is called a profunctor or a bimodule or a correspondence. There are many names for this in the literature, but here, I mean, they also mean different things, but here we want to take the viewpoint of bimodules. So a horizontal one cell, this has a source and target, a category, and then such a horizontal one cell corresponds to a bimodule. So this is a functor from C cross D up to Z. So this is what the profunctors are. And then there are two cells which are given like this. So here you have a picture of a two cell in pro. This corresponds to such a diagram here. So it has the data of F and G, lower F and G, and then there should exist some natural transformation which fits in this triangle. So this is essentially the definition of pro. And then, yeah, you should also, of course, define what composition is. So, I mean, composition in a vertical direction is clear, horizontal direction. There are some Cohen formula for this, and then for two cells, this is also more or less just composition of natural transformations and whiskering. So this is a nice exercise now to check. So you can check that the vertical truncation of pro is the two category of categories. So that's also why pro is called a proarrow equipment for this guy. But yeah, it's a nice exercise to do this. You can just check this by hand really. Now, like I said, we want to define infinity equipment, which should be like an infinity categorical variant of double categories. So the following viewpoint is very, very nice to have. So a strict double category is really a categorical object in the one category of categories. And this is something you can now interpret in the higher setting. So given an infinity category C with finite limits, you can make sense of what categorical objects in C are. So you can define an infinity category of categorical objects in C. Now, a categorical object in the infinity category of infinity categories, this would be a double infinity category. So I have some examples here, but I will not go over them. Only this is of interest for us now. So yeah, so this category is double infinity categories. So let's zoom in on what the double infinity category essentially is. So in particular, it has two infinity categories. One of them called P0. This has objects are called of P0 are called the objects of P. The one cells in P0 are the vertical one cells. Then you also have infinity category P1. Those objects are called horizontal one cells, and as the arrows in P1 correspond to the two cells of P. So this all really looks similar to what's going on classically. So essentially, the double infinity category P is this data plus some very coherent associative composition laws, which really come in the form of structure. So an example. So this is the example from before, but now in an infinity categorical setting. So there's this double infinity category, which we now will denote by pro infinity, which you can describe similarly as pro, but now you have to replace categories with infinity categories and sets with spaces. So a space is for me is a Kahn complex or an infinity groupoid or an anima or whatever you want to call it nowadays. So the vertical truncation of this pro infinity, this is the infinity 2 category of infinity categories. So that's already a very nice property. So it's a sort of enhancement of the infinity 2 category of infinity categories. So I will skip over this. So let's move on to the definition of infinity equipment. So this is really similar to, I mean, it's exactly the same as how you would define for just ordinary proarrow equipment. So let's say you have a vertical arrow from X to Y, then a companion for F. This consists of a horizontal arrow, which is capitalized F, which comes with the extra property that there exists two cells like this, and they have to compose in a certain way. So we have to have these spacing. So there are essentially only a few ways to compose these two cells. There are exactly two of them, and both ways you will want to get the identity two cells. So this is what I wrote down here. This is a very, in practice, this is very easy to check. So for instance, in the example of pro-infinity, a companion for a vertical arrow F from C to D, which is now a functor, this is given by a bimodule, capitalized F, which sits in this commutative square. So really in formulas, it's given on points by this. Okay. Now there's a nice theorem that really says that the companions are really it's not data, it's property. So there exists a double category comp, which is called the free companion pair, such that so this double category comp in particular has a vertical arrow S, such that whenever P is a double infinity category that's nice enough, you can look at map from comp to P and restrict along S to map from the free vertical arrow to P. And this is an equivalence onto the subspace of vertical arrows of P, which admit a companion. And so this is nice. And you have also other definitions, some sort of dual definitions for conjoints, which are defined similarly as companions. So now, an infinity equipment is a double infinity category such that every vertical arrow admits a conjoint and a companion. So I didn't talk about conjoints, but it's something similar to companions. Then also you have this technical condition that the vertical truncation of P is read in infinity two category. So this is some completeness condition. Then this defines a full subcategory of infinity equipment inside double infinity categories. Now it's a fact that every infinity equipment gives a formal category theory for the vertical truncation of P. Essentially, this infinity equipment gives you some Joneda structure to talk about representability, etc. So you can, I mean, a cone object should satisfy some universal property, and I mean this to define does an object of cones, you can really describe this using this universal property, and this gives you like a way to define colimits, etc. So now the canonical example of a infinity equipment is pro-infinity, and when you look at the formal category theory that this yields, this is really infinity category theory. So let's skip this theorem for now, as I'm, I think, a bit low on time. Yeah, maybe I'll just say this. So whenever P is an infinity equipment, there exists a locally fully faithful functor from the vertical truncation to the horizontal truncation, which is essentially surjective. Really, it's really the identity on objects, which is not really a nice thing to say, I would say. But, and it carries vertical arrows to their companion. So this is, if you look at pro-infinity, a bimodule, yeah, but then really, I mean, this really carries a vertical arrow to something that it represents to to a certain associated bimodule. So yeah, to end this talk, I want to state some closure properties, and this goes back to the motivation later. So I said that I was interested in finding a framework wherein relative homotopy theory and equivariant homotopy theory fit. This is essentially due to these two closure properties. So let's say you give you have infinity equipment P and infinity category T, which should be thought of as the thing by which you parameterize. Then you can construct something that is called P to the power of T. And this is again an infinity equipment, which comes with the property that the vertical truncation of this guy is really the infinity 2 category of functors from T to the vertical truncation of P. So this really gives you a formal category theory of T parameterized objects in P. And then another closure property is that this infinity category of infinity equipments is closed on a limit. Now let's, as a very first last slide, I will then give 2 examples of this. So you can apply this first closure property to pro infinity, and then you get an object which is denoted by this, and this really it's really used the correct category theory for T infinity categories as was constructed by Barwick, Dotto, Klasman, Nardin, and Shah. So that's already very nice. So if you now take T to be the G orbit category, which is something you can associate to a finite group G, you get G infinity category theory. So now the last application of this, the second point is constructing slice equipments. So whenever you have an infinity equipment P, you can construct this pullback. So here you have P to the power of the arrow, free living arrow, and then this has a projection to P, and then, well, it's just this definition. So you take the thing that selects X and you take the pullback now. And this is the slice equipment. And you can check that taking the vertical truncation is a right adjoint. So it commutes with taking this pullback. So the vertical truncation of the slice equipment is really the slice of the vertical truncation of P, where you started with. So that's a nice property. So in particular, when you apply this to pro infinity, this gives you a relative infinity category theory. So yeah, this is really, so going back to the motivation, we see that such a framework apparently exists, and yeah, there's some nice properties. So yeah, so maybe I will explain this point, why it's closed on the limit. That might not be so obvious, because it's not something you really can check by hand, but this follows from having this theory of the free companion. So sort of infinity equipments are local objects in the infinity categories, double infinity categories, and local objects are always closed on the limit. So yeah, I'm finished. Yes. So this concludes my talk. Thank you for listening.